Hi, Ken Goodman here. A few months back I made a kind of boring video where I was analyzing some different circuits for reverse battery protection for a client. I wanted to follow up on that and just quickly check out a few of those circuit options, and I'll stick to the actual battery configuration used by my client in their widget. And I'm happy to report that they did build the first prototypes with the Schottky option. They laid out the circuit board so that it could be built with the more complicated 4 MOSFET configuration, I think it was, that I came up with. But I don't think they ever got as far as building that version, which is all for the best. The actual batteries they're using are these 3.6 volt lithium thionyl chloride batteries. And I'll remind you, these batteries are they're considered dangerous, at least by Underwriters Laboratories. But, for the most part, I'm going to be sticking to configurations that are safe in the video. Maybe have a little fun at the end. We'll see. Okay, here we are in my outdoor test facility. I do have some safety equipment just in case. I thought about setting up a plexiglass shield to separate me and the camera from the batteries, but it's probably not necessary with these small D-cells. Okay, my test setup here includes a test load and 1 switch for each battery, 2 batteries in parallel when the switches are closed. The actual widget that these batteries might be powering could be some low power device like the Adafruit Itsy Bitsy there, but that's just here for decoration right now. What I've actually got wired up is just a bicolor LED and a resistor to show me when there's current flowing in the forward direction, green, and the reverse direction, red. Hard to see that from this angle, so okay, I've got this test load set up that's just an LED and current limiting resistor. It just shows me when the batteries are connected correctly. At the moment I've got 1 battery in the forward direction and 1 intentionally reversed, and the colors are not coming through very well on my camera, but when I connect the forward battery I get a green light on. When I connect the reverse battery I get the red LED lit. Again, this battery is inserted correctly. This one's inserted backwards. If I connect the correct battery to the load, the green LED lights. If I connect the reversed battery to the load, the red LED lights instead. If I connect them both at the same time with no protection, something bad could happen here. So let's just undo that. And let's add just a silicone diode to each one. Okay, so here's the setup with an ordinary general purpose silicon diode protecting each battery. One of the batteries is still plugged in backwards. What I'm really concerned about at the moment is the diode drop. So I've got the meter here showing the difference between the correctly inserted battery's positive terminal and the output of the rectifier, or the input to the load. So you can see I've got about a little over half a volt drop through the silicon diode, and of course nothing exciting happens if I connect the reversed battery, because there's a blocking diode in series with it. Okay, now let's do the same thing with Schottky diodes installed instead of the silicon diodes. They look pretty much the same, but characteristics are very different. If I connect the correctly installed battery, the LED is turning on green to indicate there's current flowing in the normal direction. The blocking diodes are going to protect me if I connect one of the batteries wrong. And with the Schottky diodes, the forward drop is about 0.17 volts in this case, so that's a lot lower voltage drop and a lot less wasted energy than with the silicon diodes. Now, with the batteries connected backwards, the Schottky is going to have more leakage current. It's going to allow more current to flow in the reverse direction than the silicon diode, but still there's not enough to light the LED. Okay, now let's try the same thing with my more complicated rectifier circuit. This is the 4 MOSFET version that I came up with for my client way back when. And again, we're going to focus on the drop across the rectifier, but in this case the rectifier circuit is on the negative side of the battery. So let me get across that with my meter. If I connect the good battery, the device comes on and I've got like 2 or 3 millivolts dropped across the rectifier. The reverse battery is blocked pretty much completely. There's no significant current flowing through the load, so the LED is not lit. I can connect both batteries with one forward and one reversed with no ill effects. Of course, this battery is not going to be doing anything. We know from the simulations this circuit has some shortcomings when the batteries are not balanced, but we're not going to worry about that right now. Now let's take a look at why we need these protections in the first place. Okay, so here I've got the batteries disconnected from the load, and the positive terminals and likewise the negative terminals of the batteries are tied together pretty securely through these terminal blocks. So I've still got one battery installed correctly and the other one installed backwards. So when I close these two switches, connecting the batteries anti-parallel, that should get pretty much maximum available current flowing through the batteries. And because I'm not quite sure what's going to happen here, I've got a fire extinguisher nearby and I'm wearing my safety goggles. Let's see what happens. Not very exciting so far. So it turns out I've only got a little less than 2.5 amps flowing in the loop. It's way more than the circuit was intended for, but not enough to do anything dramatic here. The temperature of that battery is still climbing, so I'll let it run a while. We're up to about 40 Celsius now. I can smell them. So my guess is the batteries are outgassing something now. It does seem like the temperature on the outside of the battery has leveled off around 108 Celsius. That's nowhere near hot enough to start a fire or anything like that. Let's just end the test there. Pretty anticlimactic. The battery's got hot enough to boil water, but not hot enough to melt plastics that might be used in a housing for a battery-powered device like this. But the internal pressure did cause the batteries to bulge a good bit at the bottom. Well, I hope there was something of interest in all this talk about lithium thionyl chloride batteries and parallel batteries and incorrectly installed batteries. But at least I had a little fun making it. At least I got this video out of the way, so on to something better, I hope. Hope to see you soon. Good day.